Alright, so for today I wanted to try and implement matrix multiplication and optimize it with CUDA. And I mean, this one can be thought of as a little sequel to the neural networks because this is used quite a lot there, but we only do it on CPU and it's like only matrix with vectors. But I want to generalize it a bit and maybe port it to the nn.h thing that we did a bit like 2 weeks ago. So, I mean, I guess we could start with just the simple, main.c file. So why not do that, I guess. Right, so printf hello world. And also the semicolon. And obviously the compilation, right? All right, so next step, I guess, is actually just maybe building the entire thing. So yeah, I mean, I'm just thinking we could implement everything in the main.c file, right? Or we can also think of the data structure. So it could be something like matrix m1, like matrix is gonna be the name of the data structure, and we can initialize it with 0 just to set the entire memory to 0, I guess. And yeah, probably it's gonna be a 1D array. So, and then we have the matrix for the result, which is also 0. Right, and usually the dimensions, which I guess I usually call them n, m, and p. We can make it like we have a 5 by 5 matrix multiplied with a 5 by 5 one. So it's like, yeah. And we can have some helper functions to initialize the matrices. So maybe matrix init random, it would make sense. And we pass the dimensions. And we can have the same thing for the second one. And maybe also matrix init for the other one, for the result, which is going to be, well, this one should be m and p, right? Just to keep it nice. Probably the matrix init is going to malloc the data structure. That's what I'm thinking. And then the important thing, I guess, is going to be just matrix multiplication. So matmul, and as usual we have the two inputs and then the reference to the output. I think honestly I prefer more having functions like this instead of returning the matrix. Makes it feel a bit more C-like. Maybe sure, having like a result, but like, can there be an error when you do matrix multiplication? Yeah, I mean, I guess the m could be different. So that's one error that we can get. But I mean, maybe we don't care right now about that. It's like if you have, because if you think about it, if you have different m values, would you rather, like, it's that question of can you recover from the error, or should the program just crash, right? So that's an interesting question to ask there. So yeah, whatever. So then we can just print, I guess we can print everything just to be able to check that we did the multiplication correctly. Like, why not? So let's just see. And yeah, I think we are gonna need a function for getting the like matrix at, right? And we might have to pass something like this, probably. Makes sense. Maybe with a space here. Yeah, why not? And then a new line at the end of the line, obviously. Okay, so we can just steal this one and have it for M2 as well, right? Maybe here we can have like a X and then an equal or something. And here is matrix, and this one should be N. So I think that would be the entire thing. We can do like a compiler driven development, basically. Like follow the errors and try to fix. I mean, it's TDD, but we can call it compiler because I mean this is the test basically. But yeah, so yeah, that's how I would like to have the functions look like. So yeah, now we have the option of we either use like header files, that would be nice, or just plop everything inside of here. So I mean, I guess if we use header files, we can have an include src. Let me just mark file, mark target. Sometimes it doesn't work moving files like that, but who knows. We can try to use a makefile, even though yeah, I suck at writing makefiles, but so we are gonna have like a clean probably. Yeah, so I usually like to declare source directory, include directory, but I never like write down the, let's call them flags and cc and all of that. Anyway, so source is gonna be probably, we're gonna have like a wildcard source directory .c, right? That's how you write it. Anyway, and I guess next we need obj, right? Path subst, and here we need to do something like build dir, and here is with percentage or something, or even here is percentage, right? Percentage c, percentage dot o, and then whatever src. Yeah, I think something like this. I don't remember honestly. Anyway, let's do like main, which is gonna build a main script. Well, at least here it's like $@ I think this one means the name of this thing, and then $, and up arrow, which should take everything from here. And I guess I'm not really sure if we are gonna need lmath. Maybe, who knows. So let's just leave it. So if I run make, yeah, and the other thing is, well, obviously I haven't built the object, so it's build dir. Oh, so it requires then %.c and also build dir. Yeah, and in this case we want to compile only the first argument, I guess, right? We don't want to take the entire list. Anyway, it makes sense. And here we need to include inc dir, and that's kind of all for this one, I guess. Yeah, and maybe just define just build dir by itself, which should be make dir. And yeah, obviously clean should remove main and build dir. Watch someone put build dir as /, that would be fun. Oh, what? Huh. I did an oopsie. Weird. Oh my god, it's, yeah. Well, I mean, I miss like a typo. Okay, yeah, I mean, it's fine, right? Because we don't have these things. So I guess next step is to actually create a header file with the things that we need, like the data structure and everything. So matrix.h, matrix h, define. Okay. Yeah, and also the structures, I kind of like to use typedef for them, just to not have to like worry about writing struct every time we use a structure. Matrix, and then as I said, we are gonna have like 1D array, and then some unsigned ints for the number of rows and columns. It's pretty weird how it got stuck like that. Classic Neovim issues. Sure. And then you know, the usual matrix init. I guess unsigned rows. Yeah. Well, initializing random is the same thing. Then we have this matrix add, which could take a const pointer to matrix, and then unsigned int row. Right, it takes the coordinates, let's say. And then I guess matrix set could be useful, even though we haven't used it. Could be nice to have, and float value. And obviously the important one is matrix mat multiplication. M1, M2, and the result, which is gonna be just matrix. And I used const because usually you indicate that you won't change this thing if it's const, right? That's the idea. So yeah. All right, and yeah, the next step. Well, let's check what happens if we make this thing. Oh, how about if we include matrix h? Wait 1 second. Oh, it's flags.txt. This is like a useful file if you use Neovim and the LSP is Clang. You can define some compile flags which are used by the LSP, and in this case it's gonna make matrix, right? It's gonna make it available. Mat multiplication, right? So now we can actually go to definition and stuff like that, which is pretty nice. And if we run make, it's gonna say that it doesn't know, you know, these functions at link time, I guess. Yeah. Anyway, oh, I still have the hello world. So yeah, I guess time to define those functions. So matrix.c, right? I guess first step matrix.h, and we'll see if we need anything else. Oh, that's nice. But yeah, it's weird how it looked like this, but in the other case it didn't go away. Anyway, so matrix rows. Let's initialize everything. And the data, I guess I'm gonna use malloc, right? I mean, how it's used. Anyway, so it's like rows times columns, size of float. right? And honestly, like if it fails to allocate memory, then we can just crash. And yeah, I mean, how, how do you do that? I was thinking maybe with assert, but usually it's like exit 1 or something, right? And maybe have a printf message with the classic buy more RAM. So include SDI. Like that's the only way it can happen. Obviously, if you put 1 billion rows and 1 billion columns, for sure it's gonna happen, but yeah. So matrix init random. I guess this one, we just initialize the matrix like this. And then we just yeah, we basically take like a random number, which is an integer, and we divide implicit conversion. Huh. Whatever. You need one of them to be a float, right? That's how I remember it. So yeah, whatever. We just initialize the matrix to have random values between 0 and 1, I guess. Like, why not? Why not? Then let's do the easier ones. So if we check matrix.h, we have ut and set. So ut is gonna be, unsigned int is like the number of, or I guess the row coordinate matrix.columns plus col. That's how you compute the 1D index from a 2D index, right? You multiply the how many rows you want to find with the number of columns that we have, and then you add like the final offset, which is column. Return index. So this will give us the element, yeah, from row and column. And I guess setting that value is kind of the same, except that instead of returning it, we set it. Makes sense, right? And then finally matrix matmul, which I mean, it's matrix, the prefix usually that I use, and it's the same as the header file, and then it's the name of the function. And that's like how I deal with namespaces in C. It's like, okay, the header file, or I guess maybe if the header file is huge and you have to split it, that's weird, but I can see that happening. I mean, why not? But it's kind of weird, that, honestly. Or maybe the other idea is, if the data structure is called matrix, that's the prefix for it, regardless of the name of the file. That's also an idea. But yeah, that's how I deal with, let's say, the namespace problem. Well, I guess not really problem. The JavaScript developers invented that, or did they? JavaScript doesn't have namespace. Yeah. Anyway. Yeah, so I'd like to have some asserts here. That the matrices can be multiplied. So one thing, like the first thing would be, the number of columns of the first one needs to be equal to the number of rows of the second one. That's how you do matrix multiplication, right? Yeah. Okay, and for assert, I guess include assert.h. Okay, and then we have obviously the stuff like the number of rows of the output needs to be the number of rows of the first matrix, and the same, kind of the same with the columns. Okay, and I guess another one just for the C stuff is like you have to allocate the data, right? Like you have to call to init. That makes sense. And then the part that you were waiting for, yeah, obviously the multiplication, or I guess the actual multiplication. But yeah, it's just the CPU version, so let's not get excited yet. Right, so the column, which is gonna be, here I could use matrix, like the result itself. Maybe it's gonna make it more obvious, I guess. Even though the other one was obvious as well. Yeah, and then we have float value, and this is gonna be the sum, and this part should be familiar, because we did kind of this when we did the neural network. It was the dot product, right? Like this part was the dot product, so it's matrix at, and here we need to take like row and t and multiply it with matrix at m2 t and column. Now, like this is the iterator which goes, links them together, sort of speak. I mean, kind of makes sense, right? The row, the t is the common axis, I guess. That's how nerds would call it. So t is the common thing between the two matrices, and then column. Yeah, and this should give us the like the dot product between the first row, first column, second column, and so on. Yeah, so that's how it would work. And then we just have to matrix set the value. And yeah, I mean, if we look at this thing, we can see that this part, like we have one for loop, another one, and then we have this computation here. And this one doesn't really depend on anything but like this for loop. So if you think about it, we can do each of those multiplications. Maybe I'll add some animation just to visualize it. We can do all of those multiplications in parallel. So, you know, in the ideal case, if we have rows multiplied or like rows times columns CPUs, we can have, I guess, the complexity would be just T, so just this for loop, so that would be nice. Yeah, and because this one, I mean, let's just assume that it's O n 3, right? But if we would parallelize it, it would be O of n, like perfectly, right? Because it would be n3 divided by n squared. But I mean, yeah, it's not enough CPUs. Also, there is some overhead, but you know, just theoretically, yeah. And you know, that's why in machine learning GPUs are important, because you optimize this part right here. Like this is the expensive part which gets optimized, and you know, it reduces the wait time from days to minutes, which is pretty nice. So interestingly enough, it compiled, and I guess something went wrong as usual. As usual. Huh. Yeah, as usual. Obviously, it went wrong. Okay. So let's see. I mean, I'm extremely curious what went wrong. Oh, because I put here, yeah. I'm so used to writing the for loop with I that I always put I++. Anyway, yeah, so now it looks fine. But, you know, like doing the math, multiplying this thing maybe with the first column, see if you get this value, good luck. But, you know, I'm gonna assume that it works, so yeah, it is what it is. So I guess now for the more interesting part, right, like the CUDA stuff. So first of all, let's see, we don't even have NVCC, right? It's not here, but NVIDIA SME, this one works. Okay, so we have like the drivers and stuff. And I guess if you didn't know already, I use the Nixos thing. I mean the OS itself, NeoFetch. Yeah, just got into the Nix OS stuff. And I mean, honestly, it was mainly to do with exactly this project, because on Arch the CUDA drivers were not really up, or I guess they were, yeah, they were not up to date with the CUDA toolkit for some reason. And I was like, oh my god, it's like so annoying. And just decided to try out Nix OS because it's said that you just write a flake.nix file and it works. So flake nix flake init, right? But honestly, I had a couple issue with this as well. Like, it was pretty annoying. So CUDA Nixos, right? If you search for this stuff, you get this nice, I think this one, and it's pretty neat, right? Like, make shell. It allows you to have all of these CUDA toolkit stuff, not installed necessarily on your system, but like dependencies for a single project, which I mean, kind of nice. So yeah, why not just try to do this? So I'm not gonna change that. Also, I mean, for this one, even here, like next, yeah, whatever, just to make it look like my home manager stuff, whatever. So I'm just gonna do how I do it usually, because I don't know how to do it in another way. 64 links, okay. And then packages, and I saw a lot of ways of doing this, but that's how I did it the first time, and it worked, so I haven't changed this way of doing it. Config, not sure if allow on free is needed here, but who knows. And then we have the in, okay, right, dev shells, and here I'm gonna use like system, that's why we declared it default. Okay, and now we could just copy paste this thing, right? Like, all of those we need, and then in the shell hook, not really sure why this is commented. I thought they had a reason, like explanation. Fuck knows then. I mean, it is what it is. Oh, whatever, let's just uncomment it. When I was testing it, it looked like it works if I use that. Let me just format it nicely. So I mean, the list of things, just take it from here, and then this is the shell hook, which is executed when you enter the shell. So it's like, it sets the CUDA path, it sets some LD library. It's like you had to do this thing also on Arch, but it was in my let's say, fish config file. But yeah, because of how Nix works, you have to do it, I mean, you know, Nix develop. Yeah, and the command to enter that shell is Nix develop. And then since I want to use fish as the shell, I do that. So yeah, it's gonna install all of these things. Not sure how long it takes, but yeah. Also not sure if CUDA toolkit is the same as, so if we search here CUDA toolkit, I'm not sure if it's the same as this one, but I mean, it looks like it is. We'll see, but yeah, it has to install the stuff. So oh, yeah, wanted to pause the recording, but it just finished. So, and now what's cool is that we have NVCC. Obviously, I would like to open NeoVim also with that, so Nix develop and then NVim. And you'll see that we'll need to add some extra flags and compile flags for NeoVim, but let's just write like a hello world in CUDA first. Right, so yeah, like this stuff. And compile flags. I honestly don't remember if I did this thing, but yeah, whatever. So we have the CUDA path. And so this would be the first thing that our thing needs. And then the other one is the GPU architecture, which, I mean, let's figure out what the architecture is in this test script. Right, so I don't know if we need to include CUDA runtime. Probably not, because it's a Q file or whatever, and usually I don't need to include CUDA runtime in those files. So we have the, like, these functions can throw errors. It wants the nope. Yeah, so how these functions work is how I kind of like to use C, right? You have the function, it returns the output in one of the arguments, and then as the return value it has an error. It's just like the commands from bash, because here you have the command and they return a status, so that's pretty cool. Okay, so if the error is not CUDA success, I mean, yeah, autocomplete is annoying, so I'm just gonna keep that. We are gonna printf CUDA get device failed, and then we print the CUDA get error string. Really annoying. So here we pass in the error, and we should have error message just in case. I mean, hopefully yeah, and the other thing is that I noticed, wait, where is GCC? We don't have GCC, okay. I have to add this GCC 12 because my GCC version is like 13. So yeah. Oh yeah, I guess something else here is that in the docs it says build inputs, but it should be native build inputs. I don't know what the difference is, but I guess it is what it is. So yeah, now it should work, right? And if we run the thing, yeah, we don't see any errors, right? Because we shouldn't have errors, like hopefully. So we could just CUDA device prop. That's like the properties. Device property. Oh, what's v2? I mean, I don't know. I'm not gonna use that. I'm gonna use the one that I know about. I mean, this one also returns error, but you know, you already know how to deal with it. So yeah. So let's just print the device like D, or I guess like this. Print the device name. Device prop name, and then like the compute capability is gonna be not sure if it's always like SM and then the major and minor, but I guess that's how you get this value. And see here it complains that it's SM35, right? So CUDA GPU Arch. Right, so if I go in compile flags and say here SM86, it should stop complaining. Yeah, I mean it was just LSP error, so not important anyway. So I'm not sure if it's always this format, but it looks like it is. So yeah, it is what it is. Right, so the next step obviously is to get the CUDA script, right, the kernel and everything. But I was just thinking maybe for that we can make some changes in the make file. Like for example, or maybe not, maybe just we'll see the changes that we need to make along the way. So yeah, let's just say, because we want to override this function basically, let's add an if defined matrix CPU. Let's have like a flag which enables it, right? So that's kind of what we want here. But I mean at the same time let's also change makefile. So let's say we have the CPU object files and the GPU object files. So yeah, these ones are gonna have the CPU and GPU prefix, or I guess suffix, just to make things simpler. Okay, and we also have the CUDA source files. Okay, and also the CUDA object files, and these ones are the ones compiled with NVCC basically. Yeah, I mean they're not the same as this. Yeah, like these object CPU are gonna be the ones that define this variable, or I get define, and these ones are gonna be the ones that don't define it, pretty much. Right, so we can also have an all rule, which does main CPU and main GPU. Right, CPU and main GPU. All right, and for main GPU, I leave it like this for now. Okay, works like this, but I think here we need matrix CPU like that. And obviously if it's the GPU version, we don't define it, right? I mean, we can have a define for the GPU thing, but I mean, whatever. We can, yeah, I mean, we can have it just in case we need it for some reason, but I don't think we need it. So yeah, it's fine. Okay, and the last one is for the CU. Oh, and I guess the main GPU one also needs object Q. Right. So I'll keep the CUDA files in source directory as well. Why not? But they're gonna be named like this. So here as well. Yeah, I mean, like writing the make files is really annoying. I think this should do it, except this should be NVCC, and I think like this, maybe. Yeah. Okay, I mean, let's try to make all, right? So I guess make clean. I'll just remove test, I guess, because we don't need it anymore. But yeah, let's try to make. Right, so it compiled the CPU version, right? But it failed like on the matrix GPU one. But you know, main CPU works, right? Like these are the steps to make the CPU version. It compiles the main.c file, the matrix.c file, and then it links everything basically like this. And then for GPU, it does it like this, so it doesn't define this thing, and because of that we don't have the matrix multiplication function, which I mean it's what we want because we have to do it differently now. So it didn't link. Yeah, I mean that's good in a way. So enough blue balling. Let's actually do the thing, right? So I mean threads per block, that's usually the first one, like the first thing. And I mean another important one is, you know, to just copy paste this function because it has to look the same. So let's do extern C, and then because the CUDA file is like C++, so yeah, it is what it is. So we need assert and matrix.h. So funny thing is that if we make I wanted to say that it should work. But it seems like we actually need the extra flags somewhere. I guess here. Right, we need the CUDArt thing, right? And I'm not sure if we also need to specify the path. That would suck though. Let's see. Oh. So I mean, you know, funny we done it, but now we still have to actually implement this thing, right? So yeah, I mean, if you didn't know already, like how this thing will work is that we need to copy the memory, like the data from our host to the GPU, and then copy it back. I guess do the multiplication and then copy it back. So let's define some helper things that we will need. For example, CUDA error t error, and then let's say is the data. So it's gonna be data for the first one, pointer data for the second. I mean, I hate doing pointer like this because yeah, but it is what it is. And anyway, let's CUDA malloc. So we have to pass here, like CUDA malloc also takes in, like it doesn't return the pointer like normal malloc. It actually takes in a reference. So yeah, that's one thing you have to keep in mind. So yeah, but it's just the like allocating the thing. Okay, so if the error is not CUDA success. Okay, it's not CUDA success. Then we just like printf CUDA malloc failed, and then CUDA get error exit 1. Oh, if we use printf, we need yeah, something like this. Let's do the same thing for the second matrix. Everything I think stays the same. And let's also do it for the result. Yeah, I know, weird naming convention, ABC, but it is what it is. Okay. And I guess the next step is to, as I said, copy into A and B the matrices. So also, in memcopy, I think it's pretty much the same. It's kind of the same as the memcopy from C version, but yeah. Rows times M1 columns, and yeah, you always have to not forget about the size of here when you do any operation with malloc, memcopy, and all of that, because usually that's the host device, the first cause of bugs, the leading cause of bugs, right? People forgetting about the size of, I mean, happens to me quite often. Okay, so here is the same thing. CUDA memcopy fail. And let's also do another one, right? Then we are gonna have the multiplication, so we can imagine that we'll do this one later. Right, and then we need to copy, and now it's the other way around, right? We need to copy into matrix data from DC, matrix rows, matrix columns, and this one you have to not forget to change the direction. So memcopy device to host. But yeah, other than that, it's the same. And also maybe CUDA free to not be annoying. I mean, I had once it was like a homework and people were allocating like thousands of gigabytes of GPU, and the like school cluster was full of people were also not using free, so you can imagine that testing the homeworks stopped. I mean, obviously. Right, so yeah, I guess I'm not sure if I want to start with writing the kernel or writing the call to the kernel. Like, what would make more sense? I guess writing the call first honestly makes more sense. Right, so you know the syntax, the annoying syntax. I'm just gonna write it first. Right. Yeah, so this part right here, it's when you actually call to the kernel, right? So you can think of this as these two for loops, like the outer for loops. But yeah, it's a bit more trickier than that. It's like, okay, this is gonna be a kernel that is gonna be called in parallel, right? And it's like a function that runs on the GPU like cores, which has a lot of cores. And these are the dimensions. So the grid, the block, I think there was something extra, but I mean they were pretty scuffed, but not gonna lie, dim grid. So yeah, as I said in the beginning, right? Ideally, you'd want to have a grid of rows times columns cores, right? So that's basically what grid is, a grid of cores. And the block is, well, I guess the GPU is split into blocks rather than having a single big chunk with a lot of a lot of cores. It has multiple chunks, right? So that's what block is. And then the grid dimension is how many cores each block has, so something like that. So yeah, but I mean, this is more like a coding tutorial rather than how the GPU architecture looks like, so I'm not an expert on that. I mean, just a coder, not necessarily an expert in GPUs. But yeah, just because we have multiple blocks, not a single block. Threads per block, yeah. Just because we have multiple blocks, I think it's easier to just take the number of rows that we have and split it into, let's say, okay, we use 32 threads, right? So yeah, but our what was it? It was 5 by 5, so it's pretty small. But yeah, that's the idea. It's just because we cannot really have a huge block with a lot of threads. It's like a lot of smaller blocks with number of threads. I have no idea. let's just go ahead and yeah, threads per block -1. So that would be the grid dimension, right? So how many blocks do we want to have, basically, right? So sure, ideally you can also use only one if you really want to, like one, but I think it's more efficient to use multiple blocks, right? It depends on the architecture of the GPU, obviously, like how many threads per block it has. Honestly, I always used 32, so maybe I checked at some point, but I don't remember. So yeah, like with that device properties, it's how you check it, but I don't remember, honestly, if I ever checked it, so it is what it is. Anyway, so yeah, the reason, because these guys are like three-dimensional also, so you can have like XYZ, but because we use matrices which are 2D, right? We use only 2 dimensions. Yeah, like NVIDIA CUDA grid. Let's see. I mean, oh yeah, the easy introduction, right? So yeah, so I mean, this one I saw something interesting, but you know, it's like sure it has multiple well, I guess it's a core, and each core has I guess this one is more nice to look at. It's like a grid contains multiple blocks, and each block has multiple threads, right? So that's the idea. And because of this cube here, it makes you think that it's a 3D, and it actually is a 3D structure. So yeah, I mean, you don't have to know all of that, as long as you figure out by experimenting. Like if you experiment with this stuff long enough, you'll figure it out. So don't worry about it that much. But yeah, I mean, from experience, if you understand the theory of this, it's easier to figure also out this stuff. But yeah, anyway, so let's see. So as I said, if you look at this thing, num threads per block, it's like this thing, which has multiple threads, and each thread is like a single small CPU, right? And then we have the grid, which contains multiple blocks. So yeah, that's why I said you can have like only one block, and the block can be like huge, the size of your matrix. Or you can go the other way around. You can have a huge number of blocks, which is like the size of your matrix, and then have a single thread per block. But you have to find, because I guess it's gonna look like a curve of performance, so you have to find the best spot for you. Anyway, this function, I guess I wanted to take dA, dB, dc, probably the number of rows and the number of columns. Actually, it's gonna be just the number of columns, and also the common dimension, right? The t, basically. CUDA device synchronize. Yeah, I mean, I'm just gonna call to this function. Usually, after you call to a kernel, it's good to call to this thing. Wait for compute device to finish. Oh, it also throws an error. But yeah, I mean, after you call to a kernel, it's best to know that you have to call to this thing as well. Otherwise, we can have weird, like if you call multiple kernels one after the other, that's, I guess, when it's important. But in this case, I don't know if it is. But yeah, we'll still keep it. Okay, we don't need this anymore. But we need to define the kernel now. And yeah, you guessed it right. The kernel goes outside of the extern C. Like, don't forget about that. So matrix mul kernel. And I guess, yeah, sure, I could have sent the data structure here, but it's just easier. I mean, it's the same thing if you think about it. dB. So it's yeah, it's the same thing. So I'm gonna use n, m, and p. Okay, let's try to figure out the row and the column. So the row and the column will be the row and the column which we compute. And yeah, if you remember from here, I said that this is the part that we parallelize. So this is what we want to compute, right? So we need a row and we need a column, which we compute. And yeah, this part is also a bit tricky because yeah, it uses some magic variables, which is block index. So block index is basically which block we are on right now, right? And this is the three-dimensional thing that I mentioned, right? Then we need the block dimension that is. So this is like an offset, right? I mean, it looks similar to thread index.x, to how we compute, let's say, the row and the column in our implementation somehow. But yeah, it's like the block index multiplied with how big a block is. So how big a block is refers to this grid, right? So it's this number. And then we add the thread index, which the thread index will come from the num threads per block thing. Yeah, pretty tricky though. Right, so you can think of it as like, let's say you know you are in the second block, so this one, and you know you have like 10 blocks, right? Or I guess, yeah, I'm wrong. Block dimension is like this, the number of threads per block, right? So it would be, okay, I'm at this thread, right? Or I guess this thread aligned, and the thread index is which thread inside of the block you are on. So yeah, basically, as I said in the beginning, the row is gonna be like, or I guess a single cell from the matrix is gonna be a single thread from the GPU. So that's what we want to do here. We associate one GPU core with one row, and then we do the same thing for the column, and by that we get the thread which is responsible for this single cell, so for this multiplication. Yeah, and you know, because of some random stuff, if for some reason we have, you know, too many cores used, we just ignore it. So if the row is greater than n or m, I guess it should be p though, but yeah, we just ignore it, right? And then we have to do the sum. So let me just remove the stuff that's not used, and let's see how we can actually do this stuff. So here maybe unsigned int, and we go up to, oh, I guess I was wrong. P is the common. Okay, yeah, so M here was fine. So P is the common thing here. Anyway, so value is gonna be the A plus I. Right, so we have to do what matrix at does, which is that, and then db, and I guess, yeah, here is gonna be exactly what matrix at does, so t multiplied with p plus column, and I guess this should actually be m, right? Because it's the size of, yeah. I mean, pretty weird, right? It's like the we have to look at the dimensions of a. So a is n times p, basically, and b is p times m. So here we have rho times p, and here we have d times m. Is like the second dimension. Yeah. And for the final one, dc, here we have the row, which we multiply with the second dimension, which is m in case of c, and we add column. So yeah, basically we just do what matrix at and set do, and here we set the value, right? And this should be all for the kernel. I mean, it's pretty simple. It's more difficult to figure out these indexing values, but yeah, if you just look at what matrix at does and you know the size of the, or I guess the dimensions of the matrix, shouldn't be impossible to do. So let's compare them. I mean, since we use, god damn it, I mean, I want to say since we use the same random seed, it should be the same results, but looks like something is a bit weird. Wondering why though. I mean, this should be fine. Getting the row and the column. This first indexing should also be fine because it's like which row we are on multiplied with p and then plus t to move the column, right? That makes sense. And then for this one, it's like the column stays the same, right? But we want to move vertically. Oh, yeah, I mean, I'm stupid. It's multiplication. Yeah, so we have the same results, which is pretty cool. It means that if we are wrong, at least we are wrong in both places. So yeah, you can see that the GPU one starts a bit slower. That's a bit oops, is a main. I wanted to check okay, let's see what, like, let's do a 10 by 7 by 5 or something and see if it still works. So yeah, this one, it should be a, wait, it should be a 10 by 5 one, right? So yeah, it looks like a 10 by 5 one. Same results, but the cool stuff starts when you have, let's imagine that this was like some neural network and you have 100 by 32 by 32 or something. Like this one should be more expensive on the CPU. Well, we could also time them. Yeah, I mean, oops. Well, it would start to matter when the n and p dimensions are pretty big. So like if let's say this one is, I don't know, 128 or 124 as well, right? Like that's when it starts to be noticeable. But I'm pretty sure that most of the time waste is because of printing. But if we don't print anything, it might get optimized out. Right, so we lose a bit of time there. Interesting. Well, interesting. At this point, they're kind of similar, but in like neural networks, 124 is pretty small, so you are probably gonna have 124 by 124, right? Like that's the kind of size you are gonna have. Maybe it was too much, but let's wait. I mean, it's too much. Let's make it a bit smaller. Let's do like by 32. I ain't gonna wait for that. I mean, even this one, like, should take like around 20 seconds. Well, not that much. I mean, see, it's because of printing. Huh. Let's do something else. Let's do a print of 0 0. Alright, so I would say that it should take around 10 to 20 seconds. Okay, 7 seconds, fine. And how about the GPU one? Whoa. See, like, this is where it starts to show, right? When it becomes a lot bigger. Like, when it's 1000 by 1000 matrix, it's not that interesting, right? It's kind of the same. But once you go huge, it really starts to become, let's just say, important to optimize it. Even this one was slow on the GPU. I mean, you can imagine how slow it's gonna be on the CPU. I mean, I don't even think it's worth trying to do it, but right, so now you can kind of tell why let's say if we do this kind of stuff for neural networks, right? Because on the GPU is much faster, and in neural networks you do quite a lot of matrix multiplication. Not necessarily for the learning part, but also there, obviously. But yeah, when you do inference, when you do all of that, you do quite a lot of matrix multiplications. So being able to use the GPU for that, really useful. I mean, it's still going, like 1 minute and it's not done yet. So yeah, as I said, it really starts to show once you go pretty big. And not let's just check nn.h, because I don't really remember how big the matrices were here in this one. Well, I guess it was pretty small, like 128 times 128. So yeah, it wasn't that big. But I mean, even training this wasn't that slow. But that's because we were using only 100 images. Yeah, but I mean, you know what I mean. With this kind of approach, this allows us to have larger images and maybe even more layers and all of that, because it's gonna be much faster, right? So that's pretty much the idea behind why do you want to optimize matrix multiplication with the GPU, especially for, let's say, for neural networks. That's pretty important. So yeah, I mean, hopefully you learn something from this one. And yeah, if you have suggestions of what to do, like other tutorials like this, maybe. For example, I saw someone wants to learn Golang, so you know, we can do more of that. Even though I did an API, I was thinking to do something else with Go, because yeah, we already did that pretty huge API, like have a playlist on that. So yeah, maybe a CLI tool just to test how Go works with the CLI, because I haven't done that. But yeah, I mean, you know, could be interesting. And yeah, I mean, you know, like drop a comment if you want to see maybe implementing this in the neural network, like the matrices, just to know that would be interesting. And yeah, don't forget to subscribe to get more of this kind of content. So yeah, see you in the next one. So bye.